Let's do one final example. In this one, we have a convex mirror. Remember, convex mirrors are the ones that look like this, where it's like looking at a Christmas tree ornament. So we have our ornament, 10 centimeters in diameter. So if you picture it, just your ball, it's 10 centimeters here in diameter. Acts as a convex mirror. Find the image height of a man 2 meters tall, standing 3 meters from the ornament. So when you know that you've been looking at the ornaments on the trees and you're over here, of course you're a lot bigger than the ornament, but you see a very small picture of yourself in that ornament, right? So that's kind of what we're trying to find. What is the image height that you see when you look at the ornament? So the first thing to do here, we're not required to do a diagram here, just figure it out using the equations. First thing to do is write down our givens. So you're standing 3 meters from the ornament. This is not to scale, but that's your object distance P here. So P is 3 meters. Notice I am putting units here because we were given different units and everything has to be in the same units. So the other thing that we need is we need the focal length. But to find the focal length, we need to know the radius of curvature because we know that the focal length equals the radius of curvature divided by 2. We're given that the diameter is equal to 10 centimeters. We know that the radius is the diameter divided by 2. So that means that the radius is 10 divided by 2, or 5 centimeters. So we have to divide that by 2 again to get the focal length. So 5 divided by 2 is going to be 2.5 centimeters. But now we do need to make sure and convert that to meters since our other distance is in meters. So that means that our focal length is going to be 0.0025 meters. Sorry, 0.025 meters. That's better. Okay, so once we have P and F, we know that we can find Q. We just derived it in the previous example that once you start with the mirror equation, 1 over P plus 1 over Q equals 1 over F, that once you solve for Q, that you get P times F divided by P minus F. So you can look at the previous example to see that derivation. And so that makes it a lot faster to plug in the numbers. But wait, okay, so there's a mistake here. So I didn't do it on purpose this time, but it's good because a lot of people are going to make the same mistake here. Whenever you write down the focal length of your mirror, you've got to pay attention to the sign conventions. Remember the sign conventions? It said if the focal length is behind the mirror, right? This is your mirror here, that's behind, that's negative. Convex mirrors always have negative focal lengths. So you must write that in yourself. You cannot forget it because that will definitely affect the numbers. So now we can plug in our numbers. 3 times negative 0.025 divided by 3 minus a negative 0.025. And when we do that, we get negative 0.025. That seems strange, right? We'll talk about that result in just a second. So the image distance is negative 0.025. And the image height, we know that we can get that from the magnification equation because magnification says that the magnification is negative Q over P, but it's also the image height over the object height. So if we just look at this part of the equation, we can get the image height by itself. So what we can do is we can just multiply both sides by h here, and we're going to get that the image height equals h, or let's say negative q times h over p. Now let's plug in everything that we know. We have a negative, then q we just found here times a negative 0.025. H is the object height, it said that the object was 2 meters tall here, so we didn't need it earlier, but we do need it now. That's h here. So times 2, and then divided by p. P was 3 meters. When we go ahead and plug all of those numbers in, we get 0.017 meters. So let's just look at our results real quick to make sure that they make sense. So first of all, we know that the image height is going to have to be small, so this makes sense, right? It's smaller than the size of this mirror here. And then the other thing, right, I was a little strange is, okay, how come the image distance here is the same exact value as the focal length? Is that a coincidence? What do you think? Well, hopefully you realize that it's not a coincidence, because that was the beauty of the focal point. If you remember, we talked about a long time ago, when the object is very far away from the mirror, in this case, the mirror is only 10 centimeters big here, we're 3 meters away, we're really far away. We said that that means that the rays are incoming parallel, and whenever the rays are incoming parallel, they either reflect through that focal point, or if it's a convex mirror, they appear to reflect from the focal point. So that means that all of them that are reflecting as though they are reflecting from that focal point. And the image is formed at the focal point. So that's why it happened to be the exact same thing. So that's it for this video. In the next video, we're going to start talking about lenses.